So let's have a quick review on the centroid of an element. You know that the centroid of the element is defined as defined by these two formulas. Well, Qy is the first moment about axis y, and Qx is the first moment about axis x. And what you do for an arbitrary object is that imagine you have an object in space, and you can write Qy as the integration of x dA, and you can also have Qx as the integration of y dA. These are the first moments of an arbitrary object, and this is the general formula. So when you can discretize an element into separate objects, separate well-known objects, then you can substitute the integration by summation. So what you do is first to separate the object, for example, this object, to two triangles and one rectangular object, and then write these formulas actually by a sigma in a discretized form, and then you can substitute x for each object as the x component of the centroid of that object, and y by the y component of the centroid of that object. So by this way, you will get Q first moments about each axis, and then you can make that equivalent to the centroid of the total object, the total centroid of actually the x component and y component, multiplying by the total area. So you discretize, for example, this object to two triangle and one rectangle, and then actually define the centroid of each object, and then define the distances between C1, C2, and C3 from X and Y, and sum over all of them. But this way you will get sigma X bar A and sigma Y bar A, and then put that equal to capital Y and capital X bar times the total area. So for example, if you have a simple beam with two supports, and you have an arbitrary shaped load on it, then by definition you can write here, for example, if this is the y component, then actually you can write Qy as x dA. So here it would be equivalent to W dx. So this would be equal to x bar and Okay. So what you can do is that you can integrate W in each dx elements and get the total value of the moment, and then actually you should have an x here, and then you can write qy as x bar dx. So this is the general formula, and then you can actually refer to a table. This is figure 580 of your book. You have several usual objects that you will encounter in a statics problem, and by this table you can easily get the centroid, the x bar and y bar of each object. For example, for a triangular area, we know that the y bar is equal to 1/3 of the height from the base. So it would be h over 3, and for you can have it for a semicircular or quarter circular area, for an elliptical. So whatever problem you have, you can refer to this table and get the x bar, y bar, and the area of each of these objects. So let's go and solve this problem here. For example, you have a semi-ellipse and a triangle, and then you want to calculate the centroid of this area. So you'd better first discretize this area to two objects, semi-ellipse and a triangle, and then you can refer to the table. For example, for a triangle, y bar is h over 3, and y bar is calculated from the base. So here you're going to have this is C2, and then this is going to be imagine, let me erase this. Okay, we know that it is going to be from the base. So if this is h, then this is going to be h over 3, and from the x-axis it is going to be, imagine it is a, then it is going to be a over 3. So this is what you have from this table. You have y bar h over 3. So you have to first consider the base of the object, and then from that base go the length of the height, the length of the height of the triangle over 3 from the base, and then you will get the centroid. And for semi-ellipse, you have this formula, 4b over 3 pi, and then this is going to be somewhere here, and if this is v, then this point is going to be 4b over 3 pi, right? So, well, this is for this semi-ellipse, you know that the y-axis is the axis of symmetry. So the x bar is going to be 0. So it is going to, the centroid is going to lie on the y-axis because this is the axis of symmetry. And then by referring to that table, you can get y bar as 4b over 3 pi. Here you have 26 millimeter for b, so it would be 4 times 26 over 3 pi. And for the triangle, you have 70 millimeter in the y direction, so the centroid would be 70 over 3 from the x direction. And as I told you, for the y direction also, you have h over 3, which is, h here is 247, and then h over 3 would be 247 over 3, and then from the y-axis, it is going to be 47 minus 247 over 3. Okay, let's, okay. So it is going to be 47 minus 94 over 3, which is exactly what I write here. Seventy minus 70 over 3. Why do you say that? It is going to be 1/3 of the height from the base. So it is going to be, if this is a, this is going to be a over 3. So it would be 70 over 3, right? Is that clear? Okay. I said 47 minus 2 times 47 over 3 for x. It is actually the distance from y-axis to the centroid of the triangle. So so if it is going to be the height over 3 from the base, the centroid, the C2 point, it is going to be h over 3, and then the distance from the y-axis, which is actually x bar, this is x bar for triangle. Okay. So, okay, so you calculate the distance of the centroid from each axis. C1 lies on the axis of symmetry because the ellipse is symmetrical with respect to y-axis, and C2 is also calculated. Then it's always good to draw a table when you have several objects, and write the area of each object, x bar, y bar, and then x bar a and y bar a, and calculate the area. Well, for semi-ellipse, the area you can refer to the table, and here it says it is going to be PAB over 2. So A here is 2 times 47, and B is 26. So PAB over 247, 26, and then y bar, you calculated y bar here for 26 over 3 pi, and x bar is actually 0 because it lies on the y-axis, and then you calculate x bar a and y bar a for the semi-ellipse, and then you do the same for the triangle, and at the end you have to sum the areas and sum the x bar a, y bar a for each of the objects. Well, I'm going to write here the first moment, which is x bar sigma a, which is equal to small x a. It should be y, sorry, and qy. So you have to calculate the total area, and you have to calculate x bar a for each element and sum over all of them to get qx and qy. And after you calculated these values, then you're going to have x bar as based on this formula as sigma x capital bar sigma x bar a over sigma a, and you'll get the same for y bar. Is there any question? Okay, let's have a more challenging problem now. Well, we have a cantilever beam. We have a fixed support at point A, and you have a load in the shape of a parabola, and this is the vertex, and it means that, well, the slope of the load here is 0. So if you refer to the table for different shapes, then you have for parabolic area and semi-parabolic area. And for the semi-parabolic area, it is assumed that at O, you have the vertex of the parabola. So the slope at O is 0. And this is kind of important. So you have a load of the shape parabola, and you have the maximum values at each end, and you're asked to actually determine the reactions. So this is a fixed support, and then you're going to have 3 reactions: one for the y direction, for the x direction, and a moment. So this is a static problem. So we are going to face this problem like we faced the problems in our last discussion. And so first you need to calculate the total load, because if you want to write sigma f of y, you need to calculate the total of the load on the beam. And also, if you want to calculate the moment around A, you have to calculate each component of this load and the distance from point A. So, well, what you need here, you can actually do the integration. You can write sigma m about point A as if the load density, for example, here is P, then it is going to be P x dx. So each component has a distance from point A, and then you can do the integration to calculate the moment. But well, then you have to determine what P is in terms of x, and this is a parabola, so it is going to be cumbersome. So it's better to use the principle of centroid, and actually then you can have an equivalent force for this kind of load, for this distributed load. And instead of writing this, you can write actually the x capital bar, which is the x coordinate of the centroid of this load, and then the total force. So instead of integration, you can use this formula. Well, for this should be actually P dx. So, well, the challenging part here is that you do not have a simple parabola from point A to B. So in these problems, you need to make some equivalent loading in order to calculate the force. So if you write this distributed load as the sum of these two distributed loads, in which the first one is a parabola with the maximum amount 1200, and then you have some constant distributed force with the negative sign, and the amount is 300. Then if you sum these two loads, you're going to get 900, right? If it is actually the direction of this load like this, and this is this constant distributed force which is acting upward, then if you sum these two forces, you're going to have 900 for one endpoint, for actually point B, which is 1200 minus 300. And for here, for the top force, for the downward force, you do not have any component. It is 0, and you have 300. So then here it is going to be 0 minus 300. So then if you sum these two, if you have a function, for example, for parabola, if P is Px and this has the shape of a parabola, then if you add this by a constant force, then the shape is still a parabola, but you have actually shifted the parabola upward. So then if you sum these two forces, you're going to get this, because the shape is still the parabola and the end point are the same. The end point here is 900 on point B and minus 300 on point A, and you still have the shape of a parabola. Is that clear? Any question? No questions? Okay. So with this definition, we decomposed our distributed load to two simpler loads, one constant load which is acting upward and a parabola load which is acting downward. For the first, for the top force, for the parabola acting downward, the total of this we can get from the table. The total, it is actually the area. If you refer to the table, then for a parabolic area, you actually, it is a semi-parabolic area because it is cut in half. You have the area 2AH over 3. So this is going to be the area of the parabola is 2AH over 3. So A here is 6 meter. 2, 6, and H is 1200. So it is going to be 4,800 Newton. Well, I wrote the area, but this is actually a load, so it has the units of load. So R2, which is the resultant force of the parabola, is going to be 4,800, and the resultant force for the constant load acting upward is going to be 1,800. This is a rectangle. And so now that we have the resultants of these two forces, we need to actually determine the distance that this equivalent force acts on this beam. So if you get back to the table, and look for the centroid of the semi-parabolic area for the x bar. You have 3a over 8, and so, well, from the base, actually, you have to be careful about the shape and the distances that are considered in the table. So this is going to be 3 over 8 a, right? Yes. So then you're going to have the distance from point A, 5 over 8 times a, and this is also a rectangle, so the centroid lies on the center of the rectangle, so it is going to be 3 meter because the total length is 6 meters. So you also have the distances from point A or from point B. So if you write now that we have the resultant of the forces and the distances, then we can determine the forces by writing the equilibrium equations. We have 3 unknowns, and well, let's start with the equilibrium in the x direction. We have no force in the external force in the x direction, and then ax would be 0, and then we write the equilibrium equation for the y direction, and then we have ay plus 1800, which is r1, and minus 4800, which is r2, equal to 0, and then you'll get ay as 3,000 newton. And in order to calculate ma, the moment around point A, we have to use the distances which these resultant forces have from point A. So ma is counterclockwise, so it is positive. And then you have for the 1800, which is r1, it is clockwise, so it should be R1 is counterclockwise, so it is positive, and the distance is 3 meter, and R2 acts counterclockwise around point A, clockwise around point A, so you're going to have a minus sign, and then the distance is 5/8 of the distance, so it's going to be 15 over 4 meter, and then the resultant is also 4,800. So then you will get the moment around point A, 12.6 kilonewton meter. Okay, is there any question? You mean how we decompose the initial loading into these two loads? Is that your question? Okay. Well, you know that this is a parabola, right? So, but the thing is, this is not a simple parabola. So if you want to find the centroid of this load, either you need to calculate the integration, and if you want to calculate the integration, then you need to know how this distributed load, actually what function is this distributed load, uh, uh, what function of x it is. So instead of doing that, we can actually we can write this force, this distributed load, as the sum of two forces, sum of two distributed loads. One, a simple parabola, which has 1200 at one end and 0 at the other, and all, plus a distributed load of constant force. So if you sum these two distributed loads on the right beam here, then you're going to get this parabola, right? Is there any problem with that? Because this is a constant force. If you add a constant to a parabola, you're not changing the shape of it, right? So so they are going to have the same shape and same endpoint, and then you can calculate the resultant for these two forces. Clear? Okay. Separate parabola. What do you mean by separate? We have one parabola here. You can let me. You can unmute and ask your question, Po. Okay. Is there any question about this problem? Okay, let's solve the last question. Here you have a beam with two supports, one pinned support and one roller support at point C, and you have a distributed load in the shape of a trapezoid, and well, at one end it is known that it is 300 pound per foot, and the other end it is W naught, so it is unknown. So if you want the reaction at point C, which is actually just an RY here, you don't have any constraint in the X direction. If you want this to be 0, then what should be the amount of W naught? And you're also asked to calculate the reaction at point B. So, well, again, you can calculate the first moment of this distributed load and find the resultant force and the distance of that resultant force from your point of interest. But again, you can actually divide these distributed force to two triangular distributed loads, and then refer to the table, and then calculate the distances of the resultant of these two distributed forces. So we have two triangles, and the sum would be actually the same as uh, the initial load. So so you have two triangles, and let's calculate the resultant of these distributed forces. For the top triangle, we note it as R1, and the area of the triangle, which is actually here the total force, would be 1/2 W naught, and 12 foot is the height of the triangle. And for the second triangle, you have 300 pound per feet as the actually the length of the base, and 12 foot is the height, and then can easily get to resultant forces. So now that you have the resultant force, you have to calculate the distance of this resultant force, these equivalent resultant forces. So this is a triangle. So the distance from point A for the top triangle is going to be 1/3 of the height. So if it is 12 foot, it is going to be 4 from point A, and 2/3 from point C. So it is going to be 8 foot from point C. And you calculate the same distance for R2, it is going to be 4 foot from point C, and then you have all the distances. And let me see. Yes, and so you have also two reaction forces at point B, By and Bx, and you have also Cy, and you have to first assume that C is 0 because it is mentioned in the question. And then well, if you want to calculate W naught, then you have to calculate the moment about point B, because otherwise any other point that you consider on this beam, you're going to have a moment for By and Bx around that point, and these two forces are unknown. So it would be easier to calculate the moment around point B to eliminate all the unknown forces. So let's find the moment around point B. Well, we know that the resultant of the force for the top triangle, for the first triangle, is 6 W naught, and R2 is 1,800 pound. So for the first triangle, the distance from resultant force to B would be actually the 5, which is distance from A to B, minus 4. So the distance would be 1 feet. And then well, it is going to be counterclockwise, so it is positive. R2 has distance of 3 foot, because from B to C we have 7 feet, and you're going to have 3 feet from R2 to B, and then you're going to have W naught. You will get W naught. Well, you have to consider the minus sign as well, because it is a clockwise moment. And then you will derive W naught as 900 pound per feet. and then well, because from A to B it is 5 foot, right? From A to B it is 5 foot, and then this is the 4 foot. You have R1 to A, and then we will get 1 foot from R1 to B, right? Is that clear? Okay. So now that we know W naught, we can calculate the reaction forces at B. So R1 would be 6W naught, which would be 5,400 pound. And then you can write equilibrium in a y direction, and you will get By minus 5,400 pound minus 1,800 pound, and you will get B. Now, you do not have any Bx here because there is no external force. There is no force in the x direction. So Bx is equal to 0. And that's it. Is there any question? No questions? Okay, guys, have a good one. Sure.